All right, there we go. Okay, so what I want to do today is basically do a brief recall of what you should have done at the end of Calculus 1. Okay, so like I said, this course is a natural continuation of Calculus 1. So you should have done at the end a bit of integration, and then we're just going to continue talking about this. Okay, but before I go on with more, I guess, advanced quotation mark ideas, let's talk a little bit about the basics, the definitions, to make sure that everybody is on the same page. Okay. All right, so the first thing is that I want to discuss this notion of integration. What is this? The point is that there are two types of integrals, okay? So we have indefinite integrals and definite integrals. And a priori, they may not have anything to do with each other, but then we have a theorem that's called fundamental theorem of calculus that relate the two ideas together, okay? So this is basically what I want to discuss today. So first, let's talk about indefinite integrals. And this is basically, this has to do with the notion of antiderivative. Can anybody tell me what's an antiderivative? So if I give you a function, what is an antiderivative? So given, I guess this is a little definition. So given a function y equal, let's say, little f, what do we mean by an antiderivative of this function? Anybody?
The area under a curve.
So that's a number. But what do we mean by an antiderivative?
What is that?
The opposite of the derivative.
So it's another function whose derivative is this function, right? For example, if I give you the function x, what's an antiderivative of the function x? That would be x squared over 2, right? Because if you take the derivative of x squared over 2, then you get x. Do you understand this? And that's basically what you do when you're calculating an indefinite integral. You're basically finding all possible antiderivatives of any given function, okay? So that's what we're looking for, so we need to know what it is. So given a function, little f, an antiderivative of f is another function, let's call it capital F, such that then the defining property is that if I take the derivative of capital F, I get little f. Okay, so that's what it means to be an antiderivative, and this is actually what this is like a game that we're going to be playing. I'm going to give you a function, and then I will ask you to find another function whose derivative is the one that I gave, right? So that's what indefinite integrals are about. Now, that's the definition of an antiderivative, but the point is that a function has infinitely many antiderivatives. Because as you know, if I take an antiderivative and I add a constant to it, what happens to that? What happens when you take the derivative of a constant? You get 0. Therefore, any antiderivative plus an arbitrary constant, the derivative will still be this little f. Do you understand this? So a function doesn't have one antiderivative, it has infinitely many. Okay, so it's a family of functions. So as a remark, if f is an antiderivative, of little f, then the function f of x plus c, let's call it g of x, is also an antiderivative. Where c is a constant, whatever constant you want, okay? It's a number. And a theorem that you should have studied back in Calculus 1 is the fact that, and this is now a deep statement what I'm about to say, that, okay, every function has a bunch of antiderivatives, but they all look like this, okay? So they're not weird looking. In other words, if you find one antiderivative, you basically have all of them, because all you have to do is do plus an arbitrary constant. That's it. You're not going to have any other weird function coming as an antiderivative for little f, other than being related to this capital F, okay? So these are all of them. So theorem and all antiderivatives of a little function f have the form f of x plus c for a fixed antiderivative capital F and constant c. Okay, so typically when you're being asked to find the integral of a given function, an indefinite integral, what we are asking for is, I want you to give me all possible antiderivatives. So that means that whenever you do an indefinite integration, your answer will always have to have a plus c at the end. Why? Because I'm not asking you for one antiderivative, I want to know all of them. But you already know that all of them, they have this form. You just need to find one of them, then you just do plus c. Okay? So here is a notation that we use. So notation. So we use this symbol together with, I'm writing dx here just because usually, typically we use the variable x, but if the variable is t, then you write dt and so on. So this is like a package. This symbol together with this dx, this is called a differential, but this comes together and then in here you write your function. So this is a notation, and what I'm asking for when you see this is I want to know all possible antiderivatives of the function f. Okay, so this equals all antiderivative of little f, and therefore if you're going to evaluate this, all you have to do is find one antiderivative and then you just do plus c, where c, we call this the constant of integration. Okay, that's an arbitrary constant. So this right here is called constant of integration. And this is what we mean by an indefinite integral. Okay? So, it's basically a game. I give you a function and your job is to find another function whose derivative is the one that I gave you. That's all. And then your answer is that function that you found plus c. Okay? So indefinite integral. So now let's do a couple of examples, and I'm going to use these to remind you of some basic ideas, okay? Some basic rules. All right, do you understand this? All right, so some basic rules, and the ones that you're gonna use a lot. For example, the one that appears everywhere is the power rule. So the point is that because as you can see, integration and derivative, they are kind of inverse operations to each other, right? So they're very related. There are a bunch of derivative rules that you know. Each derivative rule is going to give you an integral rule, okay? So every derivative rule has an integral counterpart, or at least most of them. So there is one derivative rule that's very important, right? Which is the derivative of a power function, x to the n, assuming that n is different than -1. So for n different than -1, what is this equal to? Actually, let me put both of them. So as you know, when n is different than -1, you calculate this one way. When n is equal to -1, you calculate this in another way. So if n is different than -1, what is the derivative of this? What do? Bring the power down, you subtract 1, right? So this is n x to the n minus 1. And what happens when n equals -1? In this case, you really have x to the -1, which is 1 over x, right? And so, oh, no. This is, it's the same thing. It's the same thing. It's just that I'm thinking in terms of the integral already. In the case of the integral is the one that has 2. So this derivative is always the same. It's always n x to the n minus 1. But I want to actually have another one here, which is what's the derivative of the natural log function. And you're going to see why I'm talking about this one now. Who remembers this? What's the derivative of ln?
1 over x.
1 over x. Now, I'm going to leave this to you as a homework to verify that actually we can improve this a little bit more. If we take the derivative of ln of absolute value of x, why am I saying improve? Because this function is better than this one. The domain of this is from 0 to infinity only. The domain of this is all real numbers except 0, right? Because remember, ln, you can only plug in positive stuff. Here, if I put absolute value, x can be negative now. The only value that is not good for x is 0, okay? But the derivative of this is actually the same as this one. So when it comes to integrals, you want to think about this rule down here. So, and now let's go ahead and let's come up with the corresponding integration formula. So this is the derivative side. Now, this is going to give us a formula on the integral side, and it has to do with the function x to the n, once again. So if you want to integrate the function x to the n, basically, I have to give you something here whose derivative equals x to the n. Following this rule, you get the following. This is x to the n plus 1 over n plus 1, and then plus c. Why? Because if I take the derivative of this guy, what do? According to our rule, we bring this down, it will cancel the n plus 1, and then you subtract 1, and so you get your x to the n. Do you understand this? Now, the point is that this rule only makes sense if n is different than -1, right? So, if n is different than -1, then we can use this. Why? What happens when n is -1? We get a 0 down here, right? But if n is -1, then we can take advantage of this, because when n is -1, our function x to the n is really x to the -1, which is 1 over x. So then the question is, what's the integral of 1 over x? So what's the integral of 1 over x? Reversing the rule, what function do you know whose derivative is 1 over x? ln of x. But again, instead of writing ln of x, we're going to take the second one. We take ln of absolute value of x. Why? Because we have a bigger domain. Okay? And the plus c, you already know what it is, why it is. Are you okay with this? So these are two important rules, and you're going to be using this rule a lot. And what's important here is that n, it doesn't have to be a natural number or an integer. It can be a real number, a fraction, whatever you want. The only restriction is, for this rule right here, n cannot be -1. Okay? All right, so we have the power rule. Then I guess there are other important rules, like for example, the constant rule that you're going to be using repeatedly. And it's the fact it comes from here. When you take the derivative of a constant times a function, let me use k. When you take the derivative of a constant times a function, what is this equal to? Remember, you can take constant out of the derivative, right? So this is just the constant times the derivative of the function. So because you can take constants out of a derivative, then you will also be able to take constants out of an integral. So that's another little rule that we're going to take advantage of, which is that the derivative of a constant times a function equals the constant times the integral of the function. Okay? So we can take constants out of an integral as well. And then similarly with addition and subtraction, you know the derivative of a sum is the sum of the derivative. So the integral of a sum is the sum of the integrals, and so on. Okay? So constant rule, and I guess I'm gonna put here also, well, number 3, sum difference rule. So you know that the derivative of the sum or the difference of two functions equals, okay, I'm gonna use primes here, the sum of derivative of the sum of difference of the derivatives. Therefore, the same thing translates to function. So if you integrate the sum of two functions or the difference, that's going to be the sum of the integrals or the difference of the integrals. Okay? For example, combining these three rules, the power rule together with the second rule and the third rule that I wrote here, you can integrate any polynomial that comes your way. Okay? So let's use that as a concrete example. So find antiderivative. And let's see, let's do something straightforward first. So let's find the integral of 2x cubed plus x minus 1 dx. All right, so here is a degree 3 polynomial, right? And we want to find this indefinite integral. According to rule number 3, to find this integral, all we have to do is find the 3 little integrals, and then we just combine it with the operation, sum and subtraction, right? And for each of these, we're going to be using power rule. Here, you're going to take advantage of the constant rule, that you can take the 2 out, and you just integrate x cubed, and so on. Do you understand this? So that's what I'm going to be doing. So from now on, I will be doing this in one shot, but right now I'm just going to illustrate the steps so you can see it. So this would be 2 times the integral of x cubed plus the integral of x minus the integral of 1. Typically, when you integrate 1, we just write dx, integral of dx, but you need to understand that there is a 1 here. Okay? Now let's integrate each of these things. So what's the integral of x cubed according to a rule? That will be x to the 4 over 4, right? It's n plus 1 over n plus 1, right? Plus integral of x squared over 2, and the integral of 1, x. Do you understand this? And then, of course, we do plus c. And now, well, in this case, we clean this up a little bit. The 2 cancel with the 4. So we get 1/2 x to the 4 plus 1/2 x squared minus x plus c. Here we basically use the 3 rules that we have above, right? We use a power rule, we use the constant rule right here in the very first term by taking the 2 out, and then we use the sum difference rule. You're going to be using this rule all over the place. Are you okay with this? All right, so let's do a couple more. How about this? Integral square root of x minus 1 square root of x dx. Now, you know, the rules are simple. The thing is that sometimes you have to get a little bit creative, okay? And there may have to be some interesting ideas that you may need to use to be able to calculate an integral, okay? So it doesn't mean that it's just applying the rule directly. Sometimes you have to modify your function and play with it a little bit before you can actually use the rules, okay? If you cannot use them directly like we did above, sometimes you have to do something to it, so that then you can use the rule. So I'm going to show you some of that in here. So let's do this, then let's say this. Okay, so here we have 3 integrals. Let's play the game. So I'm going to do 2, and then I'm going to let you try number 3 on your own, okay? So let's see, for number 2. You know, the first thing is, we see that there are 2 terms here, so we can do the integral of the square root and the integral of 1 over square root of x, then we're done, right? Because we just subtract the 2 answers. Does that make sense? So let's look at it from one at a time. How do we deal with square root of x? How do we integrate that? An exponent. Very good. We know how to deal with x to the something, right? We know how to deal with powers. So if we can rewrite that as x to some power, then we're good to go. And indeed we can. Remember, square root means x to the 1/2, right? And so when you have fractions as exponent, that really means a radical. Where the denominator is the index of your radical. Do you remember this? So what we're going to do is we're going to rewrite the problem before we compute. I'm going to write this as x to the 1/2. And what can I do with the next one? So we know what to do here. Now we use power rule, and then we're done with that little piece. So that's okay. How about the other guy? Put it in the numerator. Yeah. How? You put a negative exponent, right? So we also can write this guy as x to the 1/2 in the denominator, but then we need to bring it to the top because I need to have x to some power. I don't want to have 1 over something. You understand this? But we can easily do that by making the exponent negative. So we can also write that as x, but this time to the negative 1/2. You okay with this? Now remember, the power rule that we have applies for any exponent other than negative 1. can be a fraction, it doesn't matter. Whatever it is, we're going to use power rule unless we have -1, but then we have the special ln rule. Okay? So that covers any possible exponent. Now we integrate. So this would be x to the 1/2 plus 1 over 1/2 plus 1 minus x to the negative 1/2 plus 1 over negative 1/2 plus 1 plus c. Yes? And now you simplify. So 1/2 plus 1, that's 3/2. So that would be x to the 3/2 over 3/2 minus, and then negative 1/2 plus 1, that's 1/2. And then cleaning this up, this becomes 2 over 3, x to the 3/2 minus 2, and then x to the 1/2. When I say 1/2, I like to write it as square root of x, but you can leave it as 1/2 if you like. But then if the powers are other than 1/2, 3/2, or something else, I just leave it like that as those powers, okay? All right, questions? And by the way, you can always check your work. Like you could take, to see if you did it correctly, you can take this function, take the derivative, and then you need to obtain the original one, okay? That's how you check that you did it correctly. All right, questions? Okay, how about number 3? Let's see, give it a try. I'll give you a minute to try. Number 3, who can tell me what's the idea? What can we do for this integral? Yes?
So what I did was I separated it into two fractions, the integral of x over x squared, minus the integral of 1 over x squared.
Okay, very good. Then simplify and kind of play the same game as above, right? So again, sometimes you have to do something like, it may not be clear what to do at this point, but if you think about it a little bit, just split the fraction, and then you can simplify each little fraction, and then you will get an ln integral and then a power integral, right? So you can do that pretty easy. Good. So that becomes integral of x over x squared minus 1 over x squared. Everybody okay? Now simplifying, we have 1 over x minus, what do we do with 1 over x squared?
Change the exponent to negative and move it to the top.
We write it as x to the negative 2. And now, do we know how to do this? Yes, we do. What is this?
ln x.
Ln of absolute value of x. Remember, you should put absolute value, okay? And then this one, we use power rule, right? Okay, so we're good to go. So ln of absolute value minus, then that will be x to the negative 1 over negative 1, right? Because it's negative 2 plus 1. All right, and then this becomes ln absolute value of x plus 1 over x. And the plus is because this negative right here makes this plus, right? And x to the negative 1, we write it as 1 over x. Yes?
On a test, if we write x to the negative 1, will you mark that wrong if you wanted 1 over x?
No.
Okay.
It's fine. It's just typically you write when you give the answer. Typically, we don't like to have a negative exponent, unless we have negative fractions like that, and then if it is something too long, you don't want to be flipping everything to the denominator, so you can leave it like that. But if you see x to a negative 1, you should write as 1 over x. But if you don't do it, it's not a big deal. Okay. Questions? Now, again, it's important, plus c. Okay, you don't put the plus c, you will be taking point, you lose points because it's important. This symbol means I want to know all possible antiderivatives, not just one. Okay, it just turns out that every possible antiderivative looks like this function plus a constant. Okay, but it's important that you give me this constant. All right, how about number 4? What can we do?
I thought we would have e to the x. E to the 2 of x. I wasn't sure. I don't remember.
Okay, so let's see. First of all, you should ask yourself, how do you integrate? Let's forget about this for a second. Do we know how to integrate e to the x?
Yeah, you find the derivative of the exponent, and then you just leave the e to the 2x by x, like normally.
Yeah, but like I said, let's forget about that for a second.
Oh, okay.
If you want to do this problem, the first question that you need to ask yourself is, do I know how to deal with e to the x?
Yeah.
So for that, you need to know the derivative. Do you know the derivative of e to the x?
Yes.
What is it?
E to the x.
Therefore, what's the integral of e to the x?
E to the x.
e to the x. So we know how to deal with e to the x. Now we worry about that little 2. Now, do we know how to deal with sine?
Yeah, that's just.
So what's the integral of sine?
Negative cosine.
Negative cosine. Remember, you need to ask yourself what function you know whose derivative is sine. And you know the derivative of cosine is negative sine. So if you do minus cosine, then you will get positive sine. Yes? So we know how to integrate sine. We know how to integrate e to the x. So we should be able to manage this. So I'm going to begin by splitting this as 2 integrals. I'm going to take the 3 out in the second integral. Remember, that's a property, right? This piece, we know how to deal with that, right? So this one, the second one, is negative cosine. So we can get that out of the way immediately. So it will become negative 3 cosine of x. Now, what do we do with e to the 2x? If this was e to the x, then the answer is just e to the x, right? Now, since e to the x, the integral is itself, you could say, okay, then it's going to be e to the 2x. But then remember, you have chain rule, right? So if you write e to the 2x here, let me put it like this. If you write e to the 2x here, you're telling me that the derivative of this is equal to e to the 2x. And that's not the case. What's the derivative of this function? Let's see. So, what's the derivative of this function? E to the 2x times 2, because of the chain rule. Everybody understand this? So that 2 that comes when you take derivative, we need to get rid of it, because we don't have that 2 here. Yes? So what do? We divide by 2. This division by 2, you're basically getting rid of that 2 that you will get after you take derivative. Because remember, the idea here is that you're giving me a function whose derivative is this guy. Okay, that's what you're looking for. Now, the derivative of this e to the 2x is 2 times e to the 2x. I don't have a 2 here, so I need to get rid of it by dividing. Do you understand this? So you do that. And something else that you could do is you can artificially put the 2 here, but it was not there, so you have to divide to cancel it, right? And now you can see that what the integral of 2 times e to the 2x, that's e to the 2x. And then this over 2 is because this 1/2. You could do that little trick as well. Later, when we talk about substitution, then you will see that this naturally is the answer that you get if you make a little substitution, okay? But when the problem is simple like this, you should not be using, I mean, you can use substitution if you want, but you don't really need it for this case, okay? And then remember, plus C at the end. All right, questions? Okay, and let me just do one more, just to give you a taste that sometimes you have to think a little bit out of the box, but I have to make sure that I don't get carried away. How about, do you know, we haven't talked about substitution yet, so it's probably not fair to okay, so yeah, we haven't talked about substitution yet, so I don't want to bother you with that one. Let me do one more. How about this one? There will be a section on trigonometric integrals. So we're going to discuss all possible integrals with trigonometric functions. But right now, let's get a little taste of how that will look like. Yes?
We would use trigonometric identity to change something we can know the integral of.
Okay, very good. So what would that be?
I think tangent squared is equal to 1 plus secant squared or 1 minus secant squared.
Secant squared minus 1. So tangent squared plus 1 equals secant squared.
Okay.
Okay, very good. And why would you change it there? For example, you could also choose sine or cosine and then write a sine squared or a cosine squared, for example. But it turns out that that doesn't work. Or it works, but then you need to do more stuff. Why would you go with secant? What made you go with that identity?
I didn't originally think of the other one of doing just doing sine squared over cosine squared, but you can't take the derivative of just tangent, right?
Say that again?
You can't take the integral of just tangent, right? Because nothing derives in the tangent.
Yes, but you have to do the sine or cosine business. and then it's an ln integral. But why? My question is, why did you think of secant squared minus 1? What was the plan?
To then take the integral of that, so I can take the integral of 1 and I can take the integral of secant squared.
Okay, what's the integral of secant squared? Remember, the question that you need to ask yourself is, do you know a function whose derivative is secant squared? That's a question that you need to answer.
It's just tangent.
Very good. Do you understand this? So we don't know a function whose derivative is tangent squared, but we know a function whose derivative is secant squared. That's tangent, right? Now, can we somehow bring secant squared into the mix? Yes, we can, because we can use an identity. So the point is that you also, whenever you see integrals and you see trigonometric functions, you may need to use the identities that you learned back in trigonometry, okay? So when we go to this section, I'm gonna bring back the identities that will be important for you here, okay? But that's what I mean, that you have to think outside the box a little bit, okay? So, very good. So, now we know the plan. We're gonna turn this into secant, because then we can integrate secant squared. The 1, we can integrate that pretty easily, but then there's a little change rule that we need to take care of because of the forex, right? So, the point is that we're gonna rewrite this as secant squared minus 1. So I'm using here the identity, so recall that tangent square of u plus 1 equals secant square of u. I'm using u so that you don't get confused with the x. So, okay. And do you know how to verify this identity? This identity? Why this is true? So there is one that everybody knows, right? Which is sine square plus cosine square. What is this equal to? 1. Yes, if you don't remember this, then go back and review trigonometry. This is a very important identity. Okay? All right, now let's just play with this. Go ahead and divide both sides by cosine square. What do you get? If I divide both sides by cosine square, what do we get?
You get it.
What happens here?
That turns to tangent squared.
Tangent square. What's this?
1.
That's 1. And what's this? 1 over cosine?
Secant squared.
Sec. Right? That's how you get this. Similarly, if instead of dividing by cosine square, you divide by sine square, what do you get? You're going to get 1 plus cotangent square equals 1 over sine square. So that's cosecant square. So the same way that tangent and secant are related, cotangent and cosecant are related. Okay? So just keep that in mind. So when we talk about integrals, I typically will be talking about product of secant and tangent, but you need to understand that the same technique that we use for product of secant and tangent, you use it for product of cotangent and cosecant because they have similar behavior. Okay? Okay. Anyways, let's get this done. So now we split this as 2 integrals. So the integral of secant squared is tangent, right? So this would be tangent of 4x. But what do we need to do? And so, what do we need to do? We divide by 4, because remember, the derivative of this is secant square of 4x times 4. I don't have a 4 here, so I need to get rid of it by dividing. Okay? So, tangent of 4x over 4 minus integral of 1, x. And then plus c. Are we okay here? Okay, so that's this is what antiderivatives are, and then of course the more complicated this can get pretty tricky depending on the function that you're giving here. Okay, it could be pretty hard and it could be pretty easy. It really depends on the function. So throughout the course, we're gonna learn some techniques on how to deal with more complicated functions. But now let's switch gears a little bit and let's talk about something that's called definite integrals. Okay, that a priori may not seem to be related to this whatsoever. Okay, which has to do with the computation of area, as you were mentioning earlier. So, indefinite integral is just finding antiderivatives. Okay, that's all there is to it. Now, let's talk about definite integrals. Definite integrals, and it's not in all cases that is equal to the area under the curve of a function. That's only true when the function is positive. When the function is positive or negative over the interval, what you're calculating is the signed area, because it's actually the total area No, not total area, the net area. Because if the function is negative, you will get a negative number. The function is positive, you get a positive number, and then they will subtract each other, and they cancel out, and all of that business. Okay? If you want total area, you need to take absolute value of the function to make everything positive. Okay? So I don't want to say that this is the area on the curve of the function, because it's really the net area. Okay? But it comes from there, and that's the definition that I'm going to give you. So definite integral, the main difference is that this is a number. Okay? Before an antiderivative that was a function, this is a number. Now we have a notation for this. So given a continuous function, I'm saying continuous so that you will be able to find the definite integral. Okay? So given a continuous function, y equals f of x, its definite integral is, now here is how we define it. So we write this, the integral. So let me say definite integral. You need to know an interval over the interval. So given a continuous function f of x on an interval AB, on a closed interval AB, its definite integral is the following. So everything has to do with an interval. So the notation is very similar. Okay, it's very similar to what we had above. If you don't think about these numbers right here, A and B are numbers. If you don't think about these numbers, this is an indefinite, will look like an indefinite interval. But the moment that we put this, these are called limits of integration. Okay, this is a notation that we use for a definite integral. This is a number, and how do we define this number? If you remember, there is a little game that we play. Let me quickly give you a little picture of the game that we play here. Let's say that we have here the function f of x, and it's from A to B. Notice that I purposely roll the function to be positive, so that then you will see that when the function is positive, this number that we're calculating is really the area under the graph of the function. Okay? So what's the game that we play to define this? You have a function over the interval a comma b. We partition the interval into equal pieces, right? So we divide this into a bunch of little pieces and so on. So we call this x0, this is x1, x2, etc., xi, and then the last piece, so xn minus 1, xn. So we partition the interval AB into little pieces, and then what we do is each interval is going to be the base of a rectangle. Then we draw rectangles. Just pick a point, whichever point you want inside. I don't know, I'm going to take a typical interval here. And then I is an index that goes from 0 to n, okay? So I minus 1, xi, so just pick a point in there, whichever you want. Sometimes we pick the left point, sometimes we pick the right point or the midpoint. I'm going to call it ci, and I'm going to evaluate the function. And then that will be the height of a rectangle with base the interval xi. Okay? And we're going to do this for every little interval. In other words, I'm going to fill this graph with a bunch of rectangles. Sometimes the rectangles will be above the graph or below the graph, or a piece above, a piece below. And the idea is that if you add the areas of all of this rectangle, you approximate the area under the curve of this function. Now, the more rectangles you take, the better is the approximation. And how do you take more rectangles? By making the base more thin, like very small, okay? So the more partitions you make, the more rectangles you're gonna get. And then when we make infinitely many partitions, so infinitely many rectangles, we take the limit, that's what the area is, okay? So that's what I'm about to write. So this is gonna be equal to the limit as n approaches infinity. N is the number of rectangles that we're using. The sum from 0 to n f of ci times delta x. Now, delta x is the length of the base. So notice that this right here is the area of the ith rectangle. Rectangle is base times height. delta x is the base of the rectangle, and then f of ci is the height of the rectangle. You understand this? That's base times height. This is how we define this definite interval, okay? Let's say for delta x equals xi minus 1, and we just say, since we want all of these pieces to be exactly the same, then we just set it to be b minus a over n, okay? And that way we have the same distance here, and ci is just any point in the ith interval. If you remember when you used to do approximation, sometimes if you pick the left point, then you get the left point approximation, and the right point, the right endpoint approximation, and so on. We'll talk about numerical integration later. The reason why I'm reminding you of this, we're not going to have to bother with this, but later we're going to be calculating volumes. And to understand volumes of solids of revolution, we need to come back to this basic idea, okay? So it's good to have this process in mind. So, you know, and then if this limit exists, then we say that the function is integrable, and whatever this limit equals to, then that's the value of the integral, okay? And as you can see from the picture, if the function is positive, so note, if the function f of x is positive, then the integral from a to b of f of x equals the area under the graph of f from a to b. Okay? So you can use this to calculate area, but the function has to be positive. Because if it's negative, you will get negative numbers. Because your height is going to be negative, right? Because your rectangle is now on the x-axis. All right. So, and then, you know, for a long time, people used to calculate definite integrals like this. But then along came a very important theorem. It's called the fundamental theorem of calculus. And this is actually the one that relates this calculation with the one that we just did above. So this idea here seems to have no relation whatsoever with the game that we're playing of finding antiderivative and so on. It turns out that it has a relationship. And the secret is behind the mean value theorem. In the homework, the first couple of questions that you have in the homework, they have to do with the mean value theorem because this is very important, okay? So some true false questions, application of the mean value theorem. And the reason why it's there is because mean value theorem is at the core of the fundamental theorem of calculus. So let me mention, I was gonna do one by definition, but you're not gonna have to calculate anything by definition, so I'm not gonna waste time on that, okay? And this is very difficult, depending on the function. You can do linear functions pretty easily. You can do quadratic functions. Up to cubic function is okay. The moment that you get to higher degrees, it becomes pretty difficult to do it using this definition. And if I put a trigonometric function here, then that's it, because you will need formulas to how to write the summation, okay? And when this function is complicated, then those formulas, they get out of the way. So I'm going to introduce fundamental theorem of calculus now, and let's do some examples to see how we use it to calculate this, okay? All right, so now we use fundamental theorem of calculus to evaluate these integrals. Okay, so let me remind you of that. So as the next section, which is fundamental theorem of calculus, and basically it has two parts. Okay, so let me write down the statement. So let little f of x be a continuous function and let's suppose that we have an antiderivative, and let capital F be an antiderivative. We already know what this is. So there are several statements. The first one, and typically maybe you saw it, maybe you didn't see it in calculus 1, but there are a bunch of questions like this in the homework. Okay, so let me just quickly tell you what it is. The first one is the following. There is a function that we can define. Okay, we can define the following function. I can define, so the function g of x, I can define a function as follows. Integral from a to x of f of t dt. This is a function, and let's think about what this function is doing. Again, I'm going to do a typical graph here. Let's say we have our function f, and let's say that a is somewhere in here. Okay? So what is this function g of x doing? The moment that you give me a value for x, let's say, I don't know, some number, let's say is bigger than a, so it will be a number here. So if you give me a value for x, I'm going to put it over here. That number is being plugged in here, right? That would be the top limit of your integral. And what is it that you are really calculating? What's the output of this function?
G of x minus g of a.
So you're basically, no, that's the second part.
Oh.
So we're trying to understand what this function is. What you're doing is we have this continuous function, and then the value of this new function that we're defining actually is keeping track of all possible areas that you have under the curve, right? So we're fixing this, then give me an input, I put it as my top limit, and then the output is just this area. If it's over here, then you have to switch and then make a negative using the rules. But the point is that this is a function because giving an input is giving you an output. The output is the area under the curve of this function between these two values, whatever the x is. Do you understand this? As a function, nobody can stop you from doing that. Now, you may wonder, what are the properties of this function? It is a nice function. It is continuous. It is differentiable. What the fundamental theorem of calculus says is that this function is very nice. This is differentiable, and moreover, the derivative of this function is this guy. Okay? So this is an antiderivative of this. That's what it says. So the function g of x is differentiable, meaning you can take derivative. So, and therefore it's continuous. Remember, differentiable implies continuity. Okay? It's differentiable, and the derivative of g is the function f. Okay? It's literally what's in here. Do you understand this? Yes? Okay, so that's one version of the fundamental theorem of calculus, one part. Some books say part one, other books call it part two. It really depends. One part. Now, another part of the fundamental theorem is the one that we're going to be using, which is the one that we use to evaluate definite integrals. That says the integral from a to b of little f. To calculate this, all you have to do is find an antiderivative. We already have it, capital F. And then this is going to be the antiderivative evaluated at b minus the antiderivative evaluated at a. Okay? And so that way, we turn the calculation of area or of a definite integral, we turn into the game of finding an antiderivative. You find your antiderivative and then plug in your endpoints of your interval, subtract, and you get your answer. Okay? We typically write this, we have a notation for this. We write this as f of x, and then we do a line, and we put this. Okay? Because, you have your formula, and then we put a line, and we put the limits here. What we mean by this is whatever this function is evaluated at b minus whatever this function is evaluated at a. Okay? It's a notation that we use. Are you okay with this? So let's do examples. So, for example, let's verify. Let's take an easy function. Let's find the definite integral, and then let's calculate the area under the graph of this function, and then let's make sure that we get the same number, right? So, let's see. Number one, evaluate the integral. Then let's do integral from 0 to 1 of 2x plus 1 dx. So let's evaluate that integral. So let's call that part A, and then part B, find the area from 0 to 1 under the function 2x plus 1 using geometry. And the idea is to compare and make sure and check that the answer that we're getting A is the same as the answer that we're getting B. Okay? So That's the point of this little exercise. All right, so solution. So for part A, we want to calculate the integral from 0 to 1 of 2x plus 1 dx. Instead of writing the big limit and so on and having to deal with that, which in this case is not that bad because this is linear, we can pretty easily do this using fundamental theory of calculus. All we have to do is find an antiderivative of this guy, and then we evaluate the endpoints. So let's see, who can tell me, what's an antiderivative of 2x plus 1?
X squared plus X.
Square plus x. Everybody okay with this? And then we're going to plug in from 0 to 1. So remember what this means. This means evaluate the function at 1, so as 1 squared plus 1 minus evaluate the function at 0. Yes? So what do we get? 2. So the claim is that whatever the function is, the area under the graph from 0 to 1, it better be 2. Okay? Let's do part B and let's verify. So part B, we have the function y equals 2x plus 1. To be able to do this, we need to graph it, right? And then see what's going on. So what type of graph is this? So this is a line. And remember, to draw a line, all you need are 2 points. In this case, we can use the y-intercept and the slope to sketch this. The y-intercept is 1. So it goes here, and then the slope is 2. Is this line going up or down? It goes up. So how do we find another point? Remember, rise over wrong. We go 2 units up, 1 unit to the right, you get another point. Yes? So we do 1, 2. So right here is 3, and then 1 to the right. Here is 1. Here is another point, and then we have our line. So once you have your 2 points, you get your line. And then what are we interested in? We are interested from 0 to 1. So really what we are trying to look for is we're trying to calculate this area right here. This is what we want. Do you understand this? Okay, now let's take a look at it. What shape is this? It's a trapezoid. We can use the formula for the area of a trapezoid. If you don't remember, you can draw a line here and then split it as a rectangle and a triangle. And then find the 2 areas and add them. Okay? Let's use the area of a trapezoid, the formula for the trapezoid. So this is a trapezoid. And remember, the area of the trapezoid is the average of the bases times the height. So as base 1 plus base 2 divided by 2 times the height. So the bases are the sides that are parallel. So this is one base and this is another base. And then the height is this one right here, which is perpendicular to both bases. Okay? So how much is this base? B1? 1. How much is this base? 3. And the height? It's 1, right? Look at the picture. It's 1. So this is going to be equal to 1 plus 3 over 2 times 1. And calculating this, we get 4 over 2, which is 2. And then, of course, we get the same thing. Did you understand this? Again, this is just to check and to see that we're not really making this up. I mean, this works, okay? This really calculates the area when your function is positive, okay? Questions? Okay, so here is an integral that with the knowledge that you have, it would be actually pretty difficult to do it. Later on, when we talk about trigonometric substitutions, we're going to be able to calculate this integral by hand. But now, if I ask you this question, how do you answer? So let's see. How about the integral from -3 to 3 of the square root of 9 minus x squared? How do you answer this question? Again, later on, for example, this is going to be in the context of test number 2. This one we're going to be dealing with this type of integrals. To do this manually, you will need to use a trigonometric substitution. Okay? But right now, how else could we do this? Yes?
Oh, okay. I was gonna say
Ladies
you
first.
can make it not a square root. You can just do it by the 1/2, and then or you can do USO, but I don't know if you want to do that.
But you saw with what?
That's true. I would just put it to the 1/2 and then solve from there.
Okay. How you need to have a plan? How I mean, 1/2 and square root is the same thing. How would that help you?
I don't know. It just makes it visually better.
Okay, but that's not gonna help here. Yes.
Well, that's what I was gonna say.
Okay.
Can you just do it? Like,
You can do it. It's just that's not gonna help you.
no. Can you just like do like 3 and then minus x?
Oh no. Okay. Okay. I'm glad that you said that. I'm not glad at the same time, but I'm glad that you say it so we can get that out of the way. If you have a minus b square root, this is not square root of a minus square root of b.
That's good.
Be careful. That's what you just told me, right?
Terrible.
You cannot do that. Okay? The same way that if you have x plus y squared, this is not x squared plus y squared, right? There is that middle term plus 2xy that we're missing there. You have to be careful. So what can we do then? Well, don't forget the basics. And what is this supposed to be? What is this supposed to be?
It's curved.
This is a number, right? And what does this number represent? It's the area under the graph of whatever this function is. This is a positive function. Square root is positive quantity, right? So if you can figure out how this function looks like, then maybe it's a shape that you know, and you can calculate the area, right? So you should be asking yourself, since you don't have a mean of doing this now algebraically, we will learn the technique later on, okay? But right now we don't have it. So how do we do this? Well, let's try to see if we understand geometrically what this is. It may not look clear now that you look at it, but once I tell you, then it will be pretty straightforward. Suppose that we call this y, right? So suppose that y equals square root of 9 minus x squared. What is this? Square, very good. Square both sides, move the x squared to the other side. So we get x squared plus y squared equals 9. Do you recognize this? What is this? It's a circle. When you tell me a circle, there are two things you need to tell me. You have to tell me the center and the radius, right? What's the center? The origin. What's the radius? 3. Very good. So this right here is the equation of a circle. The center, the origin, and radius 3. Do you understand this? That's the whole thing. Now, this is not what we're doing. We're looking at this guy. But what is this? If you backtrack this, notice that if you go back, you can go from here to here, no problem. But when you go from the middle line to the first line, you will have to introduce a plus or minus, right? So what do you think that plus or minus means? Because circles are not functions. So if you put plus or minus, what you're telling me is that the positive version is the upper half of the circle, the negative version is the lower half of the circle. In other words, this right here is y equals square root of 9 minus x squared, and this down here is y equals negative square root of 9 minus x squared. So if you start with a full circle and then you go back to the equation that we have to put plus or minus. The plus means upper half, the minus means the lower half of the circle. Do you understand this? Now, in our case, we are integrating from negative 3 to 3 this function, so we are really integrating the upper half of the circle. So the answer is whatever the area of the circle is divided by 2. Yes? So what we are interested in is this part right here. This is what we want. And we recognize this as half a circle, right? So this is half the circle. So this is going to be equal to the area of the circle divided by 2. What's the area of a circle? What's the formula? It's pi r squared. What's the radius?
3.
The radius is 3. So it will be pi times 3 squared divided by 2. So the answer here is 9 pi over 2. So what I'm trying to tell you is, it's good to know what this means, because sometimes it may be very difficult, or you may not even know how to calculate the function, the integral, by using algebra. but you can reason through what's going on and then come up with the answer. Do you understand this? Okay. All right, so questions? So that was the fundamental theorem. Let me see, do I have something else I wanted to say? Okay, so let me do one more and then we're gonna go to use if we have the time. Maybe I should do use up. That way you have everything you need for the homework. Okay, if I have time, then I come back to the other one that I want to do. Okay, so everything is fine, and then we have talked about these little rules. So let me say something. It should be clear that if we want to understand how to calculate definite integrals, we cannot be relying on geometry all the time, because if we have something super weird, we don't have formula for every single check that you encounter around, right? If I draw a curve, that's a random curve, you're not gonna have a formula for that. So this is not really ideal using this method. So we really want to be able to develop some algebraic skills to calculate. But then if you want to calculate, the question boils down on finding antiderivatives, right? So right now, I'm gonna worry about how do we find antiderivatives, and then of course, once we get more techniques of antiderivatives, then we can find more interesting areas and so on, okay? So let's try to focus on that. How do we find antiderivatives? And for that, let's talk about a little technique, which is called integration by substitution, that will allow you to deal with more complex integrals, okay? Integrals that may look to be more complicated, but we transform them a little bit and then they become easy, okay? So that's the hope here. Okay, so like I said, almost every derivative rule has an integral counterpart, okay? So this use substitution comes from the chain rule. We have this important rule on derivative, which is called the chain rule. It has to do with how you take derivative of composition of functions. This rule, the consequence of that is what justifies the use of substitution, okay? So let me say here, recall chain rule. And remember, the chain rule has to do with the composition of two functions. So it tells you that if you want to take the derivative of f composed with g, how do we calculate this? This is the derivative of the outside function evaluated in the inside function, and then you need to multiply by the derivative of the inside function, right? That's what the chain rule says. Derivative of the outside evaluated in the inside times derivative of the inside. Now, this rule has an effect on the integral side, and then we get substitution. And here is how it works. So I'm going to give you the two versions, the definite version and the indefinite version, and then the definite version. So if you have the integral of some sort of composition, and then you spot the derivative of the inner function outside the integral, or almost that, you're going to see what I mean by almost derivative. So if you're off by a constant, you can always fix it and then make it work. So if you see something that has this format, then you can pretty easily calculate this, because you can do the following. You can let u be equal to g of x, and if you do that, then the derivative of u is the derivative of g. So du is going to be equal to g prime dx. You can think of this as taking derivative of u with respect of x, so du dx equals derivative of g, which is g prime. I just moved the dx over here, because now we're looking at differentials, okay? And that means that when we come back here, just replace. That's why it's called substitution. So this is going to be the integral of f of u du. Because now we change from x to the variable u, and this part right here is now my new differential du. And the hope is that now this is a simpler integral that we can calculate. Okay? That's the idea. Now, similarly, if you have a definite integral, you can play the same game. It's just that remember that you have limits of integration. So in this case, this is going to be f of u du, but then you need to adjust the limits accordingly because now your variable is no longer x, your variable is u. So you need to say, okay, when x is equal to a, u is equal to g of a. So you need to change the limits also. And when x is equal to b, u is equal to g of b. And then you keep working, and you're gonna get a number, and you're done. In the first case, you're gonna get an answer in terms of u, then you need to put back what u is equal to, because you need to give me the answer in the original variable. If the original variable is x, I get the answer in x, okay? But here, there's no need to go back. You just remember to change the limits, and then the number that you get, that's what it is. Do you understand this? Okay, so let's do some examples to see how this looks simple, but you know, we can take this to great lengths. So let's see, how about the following? So evaluate, and let's do the integral from 0 to 1 of x square root of 1 minus x squared dx. So notice that this is a little bit, this would be the same as something similar to what we had above if we didn't have this x here, okay? If we didn't have the x here, it would be complicated, but then you could recognize it as a circle, and then it's actually a quarter of a circle, right? From 0 to 1 would be a quarter of that. But it's not a circle because we have this guy here. But actually that x makes it pretty simple. So the whole point of this problem is always to recognize what substitution to make. What should be your u equal to, okay? So here is a hint. Looking at the rule, u is usually equal to whatever goes inside. So you have to spot a composition, and then u should be the inner function. But in such a way that when you take the derivative, you see it outside. So the question that you should ask yourself is, what do you see so that when you take the derivative, it's also there in your function? Or almost that. If you're off by a constant, that's not a problem. You can always fix it, okay? So for example, you should realize that there is a composition right here, the square root of 1 minus x squared, right? Your outside function is the square root function, and your inside function is this 1 minus x squared. So this will be your g. So if I let u be all of this, what's the derivative of that? The derivative is negative 2x, right? Well, I already have x out here. I'm just missing a negative 2, but that's not a problem. I can always multiply and divide by negative 2 if I want to. Do you understand this? So being off by a constant is not a problem. So that means that if I let u be 1 minus x squared, that will make this problem pretty simple. But that's a decision that you have to make. So we let u be 1 minus x squared, then du is going to be negative 2x dx. Do you understand this? If you want, you can modify the problem here by multiplying top and bottom by negative 2, and then you do a substitution this way. Or you can play with this algebraically. For example, I have x dx, so this is negative 2. I can move it over here. So that means that x dx, why am I doing that? Because that's what I have here outside. You see, x dx equals du over negative 2. So now we are ready. So this is equal to square root of u, and then x dx becomes du over 2. Do you understand this? And remember, we need to change the limits. So when x is 0, what is u equal to? What's u equal to when x is 0? 1.
1.
And when x is 1, what is u equal to? 0. Just plug in here. The substitution. Okay, and then when x is 0, u is 1. When x is 1, you get 1 minus 1 squared. 1 minus 1, u is 0. Right? These are our new limits. I'm doing this so I don't have to go back to x. And now we calculate this integral. We know how to do this. We know how to find antiderivative of square root, right? We did this already. So let's prepare this. I'm going to put the 1/2 outside, and just to introduce to you another rule. Yes.
And down on the left, you had du over negative 2.
Good. It's negative 2. That was to see if you were paying attention. Okay, good. So let me take advantage of this now. I put a 1/2 here. There's another rule. Notice that here we have 1, 0. Typically, we like the lower guy to be down here, right? We want it to have from 0 to 1. Now, you can always switch the limits of integration, but what's the price that you need to pay? You have to put a minus in front of the integral. You understand this? A negative flips the limits of integration. So I'm going to use this negative to flip the limits. Or you can flip it, that's a negative, but with this negative it becomes positive. You understand this? So this negative, I'm using it to flip the limits. So it becomes now from 0 to 1. I'm going to write it as u to the 1/2. You okay with this? And the 1/2, I just put it outside. And now we finish this. So this becomes 1/2 times. So that would be u to the 3/2 over 3/2. And then from 0 to 1. And then we evaluate. So these two cancel out. So we get 1 over 3 times, and then 1 to a 3/2, that's 1 and 0. So we get 1/3. To show you this one nice little trick. Not little trick, but just to show you that you have to get creative sometimes. And how about something like this? So, it's not clear what to do here. For example, we say, okay, I would like to make a substitution, but if I lay u with the denominator, then the u is going to be e to the x. I don't have an e to the x up here, right? You could make it work, but then you have to do some strange algebra. Let me show you something that we can do pretty quick, that will actually make this problem pretty simple. And here is the idea. The idea is that when you have an expression, you can always add and subtract what you want. So I'm going to strategically add e to the x, and then I'll take it away. So I'm going to add and subtract e to the x. Why did I do that? Because now, remember, if I had an e to the x here, it would be easy the problem, right? Because if this is your u, and then your du is right there. Okay, so I add and subtract. Why? Because you split. Now this becomes 1, and then the other one is exactly what I want, with the e to the x on top. And then we can make a substitution work pretty nice. Did you understand this? So always remember, if you don't know what to do, sometimes you may want to play this kind of trick. Add and subtract something, and that may help you with the problem. Okay, so this becomes 1 minus e to the x, or 1 plus e to the x. So separating this, the first one becomes x, and now I just have to worry about this second integral. But I already know what's going on. I don't even need to go to the substitution. The derivative of the bottom is the top, right? What happens when the derivative of the bottom is the top? That's an ln. Because remember, if you make a substitution, this would be 1 over u du, right? So this is really ln of whatever this is. So when the derivative of the denominator equals the top, that's an ln integral. So this now becomes ln of 1 plus e to the x. Notice that I didn't put absolute value, and the reason why I didn't put absolute value is because this is always a positive function. E to the x is always positive. So 1 plus e to the x is positive. There's no need to write absolute value. But when you don't know, then you have to put the absolute value. Okay, I just wanted to show you this, just to let you know that sometimes you have to get a little bit creative. Okay?